Hello, Namaste. Myself Ankita Shreya Prasad, and you are listening to along with our NCERT 11th and 12th audio video book presented by ArtSkill Passion. Chapter 8 Electromagnetic Waves 8.1 Introduction. In Chapter 4, we learned that an electric current produces magnetic field and that two current carrying wires exert a magnetic force on each other. Further, in Chapter 6, we have seen that a magnetic field changing with time gives rise to an electric field. Is the converse also true? Does an electric field changing with time gives rise to a magnetic field? James Clerk Maxwell, 1831 to 1879, argued that this was indeed the case. Not only an electric current but also a time-varying electric field generates magnetic field. While applying the Ampere circuit law to find magnetic field at a point outside a capacitor connected to a time-varying current, Maxwell noticed an inconsistency in the Ampere circuit law. He suggested the existence of an additional current called by him the displacement current. To remove this inconsistency, Maxwell formulated a set of equations involving electric and magnetic fields and their sources, the charge and current densities. These equations are known as Maxwell's equation, together with the Lorentz force formula. Chapter 4. They mathematically express all the basic laws of electromagnetism. The most important prediction to emerge from Maxwell's equation is the existence of electromagnetic waves, which are coupled time-varying electric and magnetic fields that propagate in space. The speed of the waves according to these equations turned out to be very close to the speed of light, 3 into 10 to the power 8 meter per second, obtained from optical measurements. This led to the remarkable conclusion that light is an electromagnetic wave. Maxwell's work thus unified the domain of electricity, the magnetism and light. Hertz in 1885 experimentally demonstrated the existence of electromagnetic waves. Its technological use by Marconi and others led in due course to the revolution in communication that we are witnessing today. In this chapter, we first discuss the need for a displacement current and its consequences. Then, we present a descriptive account of electromagnetic waves, a broad spectrum of electromagnetic waves stretching from alpha rays wavelength 10 to the power minus 12 m to long radio waves wavelength 10 to the power 6 meter is described. How the electromagnetic waves are sent and received for communication is discussed in chapter 15. 8.2 Displacement current. We have seen in chapter 4 that an electrical current produces a magnetic field around it. Maxwell showed that for logical consistency, a changing electric field must also produce a magnetic field. This effect is for great importance because it explains the existence of radio waves, gamma rays and visible light, as well as all other forms of electromagnetic waves. To see how a changing electric field gives rise to a magnetic field, let us consider the processes of charging of a capacitor and apply Ampere circuit law given by chapter 4. Loop integral B dl is equal to nu naught I into T. To find magnetic field at a point outside the capacitor, Figure 8.1a shows a parallel capacitor C, which is a part of circuit through which a time-dependent current I into T flows. Let us find the magnetic field at a point such as P in a region outside the parallel plate capacitor. For this, we consider a plane circular loop of radius r whose plane is perpendicular to the direction of the current carrying wire and which is centered symmetrically with respect to the wire. From symmetry, the magnetic field is directed along the circumference of the circuit loop and is the same in magnitude at all points on the loop, so that if B is the magnitude of the field, the left side of equation 8.1 is B 2 pi r. So we have now considered a different surface which has the same boundary. This is a pot-like surface, figure 8.1b, which no way touches the current but has its bottom between the capacitor plates. Its mouth is the circular loop mentioned above. Another such surface is shaped like a tiffin box without the lid. On applying Ampere's circuit law to such surfaces with the same perimeter, we find that the left hand side of equation 8.1 has not changed, but the right hand side is 0 and not u naught I, since no current passes through the surface of figure 8.1 B and C. So we have contradiction calculated one way. There is a magnetic field at a point P calculated another way. The magnetic field at P is 0. Since the contradiction arises from our use of Ampere's circuit law, this law must be missing somewhere. The missing term must be such that one gets the same magnetic field at point P, no matter what surface is used. We can actually guess the missing term by looking carefully at figure 8.1c. Is there anything passing through the surface S between the plates of the capacitor? Yes, of course. The electric field, if the plates of the capacitor have an area A and a total charge Q, the magnitude of the electric field E between the plates is Q by A by epsilon naught. The field is perpendicular to the surface S of figure 8.1c. It has the same magnitude over the area A of the capacitor plates and vanishes outside it. So what is the electric flux? E through the surface S using the gas law, it is loop integral E is equal to mod E into A is equal to 1 by epsilon naught Q by A into A is equal to Q by epsilon naught. Now if the charge Q on the capacitor plates changes with time, there is a current I is equal to dq by dt. So that using equation 8.1, we have d loop integral E by dt is equal to d by dt Q divided by epsilon naught is equal to 1 by epsilon naught dq by dt. This implies that for consistency, epsilon naught into d loop integral E by dt is equal to I. This is the missing term in Ampere's circuit law. If we generalize this law by adding to the total current carried by conductors through the surface another term which is epsilon naught times the rate of change of electric flux through the same surface, the total has the same value of current I for all surfaces. If this is done, there is no contradiction in the value of B obtained anywhere using the generalized Ampere's law. B at the point P is non-zero no matter which surface is used for calculating it. B at point P outside the plates. Figure 8.1a is the same as at the point M just inside, as it should be. The current carried by conductors due to flow of charges is called conduction current. The current given by equation 8.4 is a now term and is due to changing electric field or electric displacement, an old term still used sometimes. It is therefore called displacement current or Maxwell's displacement current. Figure 8.2 shows the electric and magnetic field inside the parallel plate capacitor discussed above. The generalization made by the Maxwell then is the following. The source of magnetic field is not just the conduction electric current due to flowing charges. but also the time rate of change of electric field. More precisely, the total current I is the sum of conduction current denoted by IC and the displacement current denoted by ID is equal to epsilon naught d loop integral E by dt. So we have I is equal to IC plus ID is equal to IC plus epsilon naught d loop integral E by dt. In explicit terms, this means that outside the capacitor place we have only conduction current IC is equal to I and no displacement current, that is ID is equal to 0. On the other hand, inside the capacitor there is no conduction current, that is IC is equal to 0, and there is only displacement current, so that ID is equal to I. The generalized and correct Ampere circuit law has the same form as equation 8.1, with one difference: the total current passing through any surface of which the closed loop is the perimeter is the sum of the conduction current and the displacement current. The generalized law is loop integral B into dl is equal to nu naught IC is equal to nu naught epsilon naught d loop integral E by dt and is known as Ampere's Maxwell law. In all respects, the displacement current has the same physical effects as the conduction current. In some cases, for example steady electric fields in a conducting wire, the displacement current may be 0 since the electric field E does not change with time. In other cases, for example the charging capacitor above, both conduction and displacement currents may be present in different regions of space. In most of the cases, they both may be present in the same region of space. As there exists no perfectly conducting or perfectly insulating medium. Most interestingly, there may be large regions of space where there is no conduction current, but there is only a displacement current due to time varying electric fields. In such a region, we expect a magnetic field through there is no conduction current source nearby. The prediction of such a displacement current can be verified experimentally. For example, a magnetic field, say at a point M between the plates of the capacitor in figure 8.2a, can be measured and is seen to be the same as the just outside at P. The displacement current has literally far-reaching consequences. One thing we immediately notice is that the laws of electricity and magnetism are now more symmetrical. Faraday's law of induction states that there is an induced EMF equal to the rate of change of magnetic flux. Now, since the EMF between 2 points 1 and 2 is the work done per unit charge in taking it from 1 to 2, the existence of an EMF implies the existence of an electric field. So we can rephrase Faraday's law of electromagnetic induction by saying that a magnetic field changing with time gives rise to an electric field. Then the fact that an electric field changing with time gives rise to magnetic field is the symmetrical counterpart and is a consequence of the displacement current being a source of magnetic field. Thus time-dependent electric and magnetic fields give rise to each other. Faraday's law of electromagnetic induction and Ampere's Maxwell law gives a quantitative expression of this statement, with the current being the total current as in equation 8.5. One very important consequence of this symmetry is the existence of electromagnetic waves, which we discuss qualitatively in the next section. 8.3 Electromagnetic waves. 8.3.1 Source of electromagnetic waves. How are electromagnetic waves produced? Neither stationary charges nor charges in uniform motion, steady currents can be sources of electromagnetic waves. The former produces only electrostatic fields, while the latter produces magnetic fields that, however, do not vary with time. It is an important result of Maxwell's theory that accelerated charges radiate electromagnetic waves. The proof of the basic result is beyond the scope of this book, but we can accept it on the basis of rough qualitative reasoning. Consider a charge oscillating with some frequency. An oscillating charges is an example of accelerating charges. This produces an oscillating electric field in space, which produces an oscillating magnetic field, which in turn is a source of oscillating electric field, and so on. The oscillating electric and magnetic fields thus regenerate each other, so to speak, as the wave propagates through the space. The frequency of the electromagnetic wave naturally equals the frequency of oscillation of the charges. The energy associated with the propagating waves comes at the expense of the energy of the source, the accelerated charge. From the preceding discussion, it might appear easy to test the prediction that light is an electromagnetic wave. We might think that all we need to do was to set up an AC circuit in which the current oscillates at frequency of visible light, say yellow light, but alas, that is not possible. The frequency of yellow light is about 6 into 10 to the power 14 Hz, while the frequency that we get even with modern electronic circuit is hardly about 10 to the power 11 Hz. This is why the experimental demonstration of electromagnetic wave had to overcome in the low frequency region. The radio wave region, as in Hertz's experiment 1887, Hertz's successful experiment test of Maxwell's theory created a sensation and sparked off other important works in this field. Two important achievements in this connection deserve mention. 7 years after Hertz, Jagdish Chandra Bose, working at Calcutta, now Kolkata, succeeded in producing and observing electromagnetic waves of much shorter wavelength, 25 mm to 5 mm. At experiments like that, Hertz was confined to the laboratory. At around the same time, Guglielmo Marconi in Italy followed Hertz's work and succeeded in transmitting electromagnetic waves over distances of many kilometers. Marconi's experiments marks the beginning of the field of communication using electromagnetic waves. 8.3.2 Nature of electromagnetic waves. It can be shown from Maxwell equations that electric and magnetic fields in an electromagnetic wave are perpendicular to each other and to the direction of propagation. It appears reasonable see from our discussion of the displacement current. Consider figure 8.2. The electric field inside the plates of the capacitor is directed perpendicular to the plates. The magnetic field this gives rise to VR displacement current is along the perimeter of a circle parallel to the capacitor plates. So B and E are perpendicular in this case. This is a general feature. In figure 8.4, we show a typical example of a plane electromagnetic wave propagating along the Z direction. The fields are shown as a function of the Z coordinate at given time t. The electric field Ex is along the x-axis and varies sinusoidally with Z at a given time. The magnetic field By is along the y-axis and again varies sinusoidally with Z. The electric and magnetic field Ex and By are perpendicular to each other, and to the direction Z of propagation we can write Ex and By as follows. Ex is equal to E naught sine kz minus omega t. By is equal to B naught sine kz minus omega t. Here k is related to the wavelength lambda of the wave by the usual equations. K is equal to 2 pi lambda and omega is the angular frequency, k is the magnitude of the wave vector or propagation vector k. and its direction describes the direction of propagation of the wave. The speed of propagation of the wave is omega by k. Using equation 8.7a and b for Ex and By and Maxwell equation, one finds that omega is equal to ck, where c is equal to 1 by root over nu naught epsilon naught. The relation omega is ck is the standard one for wave. See for example section 15.4 of class 11th physics textbook. This relation is often written in terms of frequency. V is equal to omega by 2 pi and wavelength lambda is equal to 2 pi by k, as 2 pi V is equal to c 2 pi by lambda, or V lambda is equal to z. It is also seen from Maxwell equation that the magnitude of the electric and the magnetic field in an electromagnetic wave are related as B naught is equal to E naught by C. We here make remarks on some features of electromagnetic waves. They are self-sustaining oscillations of electric and magnetic fields in free space or vacuum. They differ from all other waves we have studied so far in respect that no material medium is involved in the vibration of the electric and magnetic fields. Sound waves in air are longitudinal waves of compression and rarefaction. Transverse elastic sound waves can also propagate in a solid which is rigid and that resists shear. Scientists in the 19th century were so much used to the mechanical picture that they thought that there must be some medium pervading all space and all matter, which responds to electric and magnetic fields just as elastic medium does. They called this medium ether. They were so convinced by the reality of this medium that there is even a novel called The Poison Belt by Sir Arthur Conan Doyle, the creator of the famous detective Sherlock Holmes, where the solar system is supposed to pass through a poisonous region of ether. We now accept that no such physical medium is needed. The famous experiment of Michelson and Morley in medium is needed. The famous experiment of Michelson and Morley in 1887 demolished conclusively the hypothesis of ether. Electric and magnetic fields oscillating in space and time can sustain each other in vacuum. But what if a material medium is actually there? We know that the light, an electromagnetic wave, does propagate through glass. For example, we have seen earlier that the total electric and magnetic field inside a medium are described in terms of permittivity epsilon and magnetic permeability nu. These describe the factors by which the total fields differ from the external fields. These replace epsilon naught and nu naught in the description to electric and magnetic fields in Maxwell's equation, with the result that in a material medium of permittivity epsilon and magnetic permeability nu, the velocity of light becomes v is equal to 1 by root over nu by epsilon. Thus, the velocity of light depends on electric and magnetic properties of the medium. We shall see in the next chapter that the refractive index of one medium with respect to the others is equal to the ratio of velocities of light in the two media. The velocity of electromagnetic waves in free space or vacuum is an important fundamental constant. It has been shown by experiments on electromagnetic waves of different wavelengths that this velocity is the same, independent of wavelength, to within a few meters per second. Out of a value of 3 into 10 to the power 8 meter per second, the constancy of the velocity of EM waves in vacuum is so strongly supported by experiments, and the actual value is so well known now that this is used to define a standard of length.
namely the meter, is now defined as the distance traveled by light in vacuum in a time 1 by c seconds. 2.99792458 into 10 to the power 8 whole to the power minus 1 seconds. This has come about for the following reasons. The basic unit of time can be defined very accurately in terms of some atomic frequency, that is, frequency of light emitted by an atomic in a particular process. The basic unit of length is harder to define as accurately in a direct way. Earlier measurement of c using earlier units of lengths, meter, rods, etc. converts to a value of about 2.9979246 into 10 to the power 8 meter per second. Since c is such a strongly fixed number, unit of length can be defined in terms of c and the unit of time. Hertz not only showed the existence of electromagnetic waves but also demonstrated that the waves which had wavelength 10 million times that of the light waves could be diffracted, refracted and polarized. Thus, he conclusively established the wave nature of the radiation. Further, he produced stationary electromagnetic waves and determined their wavelength by measuring the distance between two successive notes. Since the frequency of the wave was known, being equal to the frequency of the oscillator, he observed the speed of the wave using the formula v is equal to v by lambda and found that the wave traveled with the same speed as speed of light. The fact that electromagnetic waves are polarized can be easily seen in the response of a portable AM radio to a broadcasting station. If an AM radio has a telescopic antenna, it responds to the electric part of the signal. When the antenna is turned horizontal, the signal will be greatly diminished. Some portable radios have horizontal antenna, usually inside the case of radio, which are sensitive to the magnetic component of the electromagnetic wave. Such a radio must remain horizontal in order to receive the signal. In such cases, responses also depend on the orientation of the radio with respect to the station. Do electromagnetic waves carry energy and the momentum like other waves? Yes, they do. We have seen in chapter 2 that in a region of free space with electric field E, there is an energy density epsilon naught E squared by 2. Similarly, as seen in chapter 6, associated with a magnetic field B is a magnetic energy density B squared by 2 epsilon naught, as electromagnetic waves contains both electric and magnetic fields. There is a non-zero energy density associated with it. Now consider a plane perpendicular to the direction of propagation of the electromagnetic waves. If there are on this plane electric charges, they will be set and sustained in motion by the electric and magnetic fields of the electromagnetic waves. The charges that acquire energy and momentum from the waves. This just illustrates the fact that an electromagnetic wave, like other waves, carries energy and momentum. Since it carries momentum, an electromagnetic wave also exerts pressure called radiation pressure. If the total energy is transferred to the surface and T is U, it can be shown that magnitude of the total momentum delivered to this surface for complete absorption is P is equal to U by C. When the sun shines on your hand, you feel the energy being absorbed from the electromagnetic waves. Your hands get warm. Electromagnetic waves also transfer momentum to your hand, but because C is very large, the amount of momentum transferred is extremely small and you do not feel the pressure. In 1903, the American scientist Nicholas and Hull succeeded in measuring radiation pressure of visible light and verified equation 8.12, it was found to be of the order of 7 into 10 to the power minus 6 Newton meter square, thus on a surface of area 10 to the power 10 centimeter square. The force due to radiation is only about 7 into 10 to the power minus 9 Newton. The great technology importance of electromagnetic waves stems from their capacity to carry energy from one place to another. The radio and TV signals from broadcasting stations carry energy. Light carries energy from the sun to the earth, thus making life possible on earth. 8.4 Electromagnetic spectrum. At the time Maxwell predicted the existence of electromagnetic waves, the only familiar electromagnetic waves were the visible light waves. The existence of ultraviolet and infrared waves was barely established. By the end of the 19th century, X-rays and gamma rays had also been discovered. We now know that electromagnetic waves induce visible light waves. X-rays, gamma rays, radio waves, microwaves, ultraviolet and infrared waves. The classification of EM waves according to frequency is the electromagnetic spectrum. There is no sharp division between one kind of wave and the next. The classification is based roughly on how the waves are produced and or detected. We briefly describe these different types of electromagnetic waves in order of decreasing wavelengths. 8.4.1 Radio waves. Radio waves are produced by the accelerated motion of charges in conducting wires. They are used in radio and television communication systems. They are generally in the frequency of range from 500 kHz to about 1000 MHz. The AM amplitude modulated band is from 530 kHz to 1710 kHz. Higher frequencies up to 54 MHz are used for short wave bands. TV waves range from 54 MHz to 890 MHz. The FM frequency modulated radio band extends from 88 MHz to 108 MHz. Cellular phones use radio waves to transmit waves communication in the ultra high frequency UHF band. How these waves are transmitted and received is described in chapter 15. 8.4.2 Microwaves. Microwaves, short wavelength radio waves with frequencies in the gigahertz (GHz) range, are produced by special vacuum tubes called klystrons, magnetrons, and gun diodes. Due to their short wavelengths, they are suitable for the radar system used in aircraft navigation. Radar also provides the basis for the speed guns used to time force bells, tennis serves, and automobiles. Microwaves ovens are interesting domestic application of these waves. In such ovens, the frequency of the microwaves is selected to match the resonant frequency of water molecules so that energy from the waves is transferred efficiently to the kinetic energy of the molecules. This raises temperature of any food containing water. 8.4.3 Infrared waves. Infrared waves are produced by hot bodies and molecules. This band lies adjacent to the low frequency or long wavelength end of the visible spectrum. Infrared waves are sometimes referred to as heat waves. This is because water molecules present in most materials readily absorb infrared waves. Many other molecules, for example CO2, NH3, also absorb infrared waves. Many other molecules, for example CO2, NH3, also absorb infrared waves. After absorption, their thermal motion increases. That is, they heat up and heat their surroundings. Infrared lamps are used in physical therapy. Infrared radiations also play an important role in maintaining the Earth's warmth or average temperature through the greenhouse effect. Incoming visible light, which passes relatively easily, greenhouse effect. Incoming visible light, which passes relatively easily through the atmosphere, is absorbed by the Earth's surface and re-radiated as infrared longer wavelength radiations. This radiation is trapped by greenhouse gases such as carbon dioxide and water vapor. Infrared detectors are used in Earth satellites, both for military purposes and to observe growth of crops. Electronic devices, for example semiconductors, light emitting diodes, also emit infrared and are widely used in the remote switches of household electronic systems such as TV sets, video recorders, and hi-fi systems. 8.4.4 Visible rays. It is the most familiar of electromagnetic waves. It is the part of the spectrum that is detected by human eye. It runs from about 4 into 10 to the power 14 Hz to about 7 into 10 to the power 14 Hz, or a wavelength range of about 700 to 400 nanometer. Visible light emitted or reflected from objects around us provides us information about the world. Our eyes are sensitive to this range of wavelengths. Different animals are sensitive to different range of wavelengths. For example, snakes can detect infrared waves, and the visible range of many insects extends well into the ultraviolet. 8.4.5 Ultraviolet rays. It covers wavelengths ranging from about 4 into 10 to the power minus 7 meter 400 nanometer down to 6 into 10 to the power minus 10 meter 0.6 nanometer. Ultraviolet UV radiation is produced by special lamps and very hot bodies. The sun is an important source of ultraviolet light, but fortunately most of it is absorbed in the ozone layer in the atmosphere at an altitude of about 40 to 50 km. UV light in the large quantities has harmful effects on humans. Exposure to UV radiation induces the production of more melanin, causing tanning of the skin. UV radiation is absorbed by ordinary glass. Hence, one cannot get tan or sunburn through glass windows. Welders wear special glass goggles or face masks with the glass windows to protect their eyes from large amount of UV produced by welding acres. Due to its shorter wavelengths, UV radiation can be forced into very narrow beams of high precision applications such as LASIK laser assisted in situ keratomyelinosis eye surgery. UV lamps are used to kill germs in water purifiers. Ozone layer in the atmosphere plays a protective role, and hence its depletion by chlorofluorocarbons CFCs gas such as freons is a matter of international concern. 8.4.6 X-rays. Beyond the UV region of electromagnetic spectrum lies the X-ray region. We are familiar with the X-rays because of its medical applications. It covers wavelength from about 10 to the power minus 8 meter 10 nanometer down to 10 to the power minus 13 meter and 10 to the power minus 4 nanometer. One common way to generate X-rays is to bombard a metal target by high energy electrons. X-rays are used as a diagnostic tool in medicine and as a treatment for certain forms of cancer. Because X-rays damage or destroy living tissues and organisms, care must be taken to avoid unnecessary or overexposure. 8.4.7 Gamma rays. They lie in the upper frequency range of the magnetic spectrum and have wavelength of from about 10 to the power minus 10 meter to less than 10 to the power minus 14 meter. This high frequency radiation is produced in nuclear reactions and also emitted by radioactive nuclei. They are used in medicine to destroy cancer cells. Table 8.1 summarizes different types of electromagnetic waves, their production and detection. As mentioned earlier, the demarcation between different regions is not sharp and there are overlaps.
Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.